This Zoom session is being brought to you by the fractal odd dyadic horizon BL. Okay, today we will be going over 3.5 complex roots in the fundamental theorem of algebra, and also 3.6 rational functions. All right, so to begin. All right, the fundamental theorem of algebra. Fine name isn't that okay? Whatever. It says every polynomial with complex coefficients has at least one complex root, c, such that p of c equals 0. And therefore, when you do the division algorithm, that means that p of x equals x minus c times a quotient q of x. So, and if you so that's called factoring out a root. Then if you take q of x, it's a polynomial. It has at least one complex root, so factor out that and keep going until you factored out every root, and you get what's called a complete factorization, where polynomial equals a number times x minus c1 times x minus c2 times x minus cn, where a, c1, c2 up to cn are complex numbers. c1 through cn are the roots. A is a scale factor. So that means that every degree polynomial, a polynomial degree, and has n roots if you count complex roots and you count multiple roots multiple times. So for example, x minus I times x plus I times x minus 2 quantities squared has the roots I minus I and the root 2 twice, so it has 4 roots. So if you double count double roots. Now, if they're all coefficients are real, so an equals an bar, an minus 1 bar equals an minus 1, and so on, so they equal their own conjugates, then it follows from the arithmetic that p of x bar equals p of x quantity bar. So it turns conjugates into conjugates. So if p is 0 at number c, then it's also 0 at the number c conjugate. So if its coefficients are real, then the complex roots come in conjugate pairs, c and c conjugate. So for example, here's x squared plus 1 times x squared plus 4, which factors in x minus I times x plus I times x minus 2i times x plus 2i. So this polynomial has roots at plus 1, minus 1, 2i, and minus 2i. All right, so let's do some examples. Finding the roots and the factor x to the 4th plus 4x squared. Okay, we start with that. We can obviously factor out an x squared. That's an x minus 0 quantity squared, so you'll have 0 twice. X squared plus 4, well, that's x squared plus 2 squared. And a sum of squares equals a complex number times conjugate. In this case, x minus 2i times x plus 2i. Yeah, if you multiply this out, you'll get x squared plus 4. In general, x squared plus a squared is x minus ia times x plus ia. Whatever. So, okay, this is 0 when x squared is 0, so 0 is a double root. Or when x minus 2i is 0, so x equals 2i. Or when x plus 2i is 0, or x equals negative 2i. So these are the roots. Minus 2i plus 2i and 0 counted twice. Here we have x squared plus x to the 4th plus 2x squared plus 1. Factor that. Okay, well, this 1, 2, 1 looks like a sum of squares, and because of the powers of x to the 4th, it's x squared plus 1 all squared. And then, as before, x squared plus 1 is x squared plus 1 squared, which factors into conjugate pairs. X minus I times x plus I. And then square it, so you get x minus I times x plus I again twice, because of the second power 2 factor. So it has x equals I as a root twice, and x equals negative I as a root twice. So it has 2 double roots. So therefore, 4th degree. You have x to the 3rd plus x squared plus 9x plus 9. Okay, this factors by groups, because these two have a common factor of x squared times x plus 1. And these two have a common factor of 9 times, well, what do you know, x plus 1 again. So, okay, you pull out a factor here of x plus 1, left with x squared plus 9. And this also is a sum of x squared plus 3 squared, which you can write as a product of conjugates. So x minus 3i times x plus I times x plus 1, which you can also write as x minus negative 1. So the roots are 3i to make this factor 0, or negative 3i to zero out this factor, or x equals negative 1 to factor out this factor. So 3 roots, which fits a third degree polynomial. Here's x to the fourth plus 3x squared minus 4. Again, this is all on x squared, so we can think of it as a quadratic in x squared. X squared plus something times x squared times something else, where the two somethings multiply to -1 and add to 3, and 4 and -1 work. X squared plus 4 times x squared minus 1. 4x squared minus x squared is 3x squared. 4 times -1 is -4, and x squared times x squared is x to the fourth. So this factors into x squared plus 4 times x squared minus 1. And okay, x squared minus 1 is a difference of squares, x minus I times x plus I. X squared plus 4, x squared plus 2 squared, is a sum of squares, so we can write that as a conjugate product, x plus 2i times x minus 2i. Okay, so, and all right, then we can read off the roots from here. Minus 2i makes this factor 0, plus 2i makes this 0, 1 makes this 0, -1 makes this 0, so those are the roots. Plus and minus 2i, plus and minus 1. 4 roots for a fourth degree polynomial. Now let's run this backwards. Here they ask for a polynomial of degree 2 with these two roots, 1 plus I and 1 minus I. All right, so x minus 1 root times x minus the other root, that will do. X minus 1 plus I times x minus 1 minus I. Okay, so then let's expand it. Minus the sum, that's so okay, you can expand it out. FOIL x times x is x squared. Inner outer is x times minus 1 times x times minus 1 minus I here, or minus 1 plus I times x, or 1 minus I times 1 plus I. Okay, then we expand these two, and this is this difference of a product of a difference times the sum, and that factor that you can multiply that out. And okay, here a bunch of terms, and after a bunch of cancellations, you get x squared minus 2x plus 2, and that does it. Let's find all the roots of x squared minus 3x squared plus 3x minus 2. Well, all right. This is the point where using the rational roots there makes a great deal of sense. So let's go. We need factors of -2. The rational roots would be a divisor of -2 divided by a divisor of 1. There are only 4 possibilities, plus and minus 1 and plus and minus 2. So, okay, starting with 2, you work out the synthetic division, find out that 2 is indeed a root of the polynomial. So the polynomial is x minus 2 times, and you read off this, x squared minus x plus 1. Okay, this is a quadratic. To solve it, we set equal to 0, use the quadratic formula. After a bit of churning is a half plus or minus I root 3 over 2. So we have the 3 roots of a third degree polynomial. 2, a half minus I root 3 over 2, and a half plus I root 3 over 2. There we are. Here we have x to the fifth minus x to the fourth plus 7x cubed minus 7x squared plus 12x minus 12. Well, I can see there's some repeating. 1 minus 1, 7 minus 7, 12 minus 12. So it looks eminently factorable by groups. We rewrite this. For these two terms, x to the fifth minus x to the fourth, we pull out a factor of x to the fourth. For these two terms, we pull out a 7x squared. For these two terms, we pull out a 12. They all have an x minus 1 in common, so we pull that out, x minus 1 times x to the fourth plus 7x squared plus 12. Now this looks like another one of those quadratics of x squared things. All we need to factor are two numbers whose product is 12 and whose sum is 7. 3 and 4 fit the bill. So the polynomial is x minus 1 times x squared plus 3 times x squared plus 4. Now, okay, x squared plus a square is x minus I. X squared plus a squared is x minus IA times x plus IA. So here, a squared is 3, so a must be root 3. There, a squared is 2, so a must be 2. So this becomes x minus I times, and this multiplies out to x minus I root 3 times x plus I root 3. And this factors out to x minus I2 times x plus I2. Okay, so we have 1, 2, 3, 4, 5 factors befitting a fifth degree equation. The roots are when this one of these factors is 0. X minus 1 is 0 at 1. This is 0 at I root 3. This is 0 at minus I root 3. This is 0 at I times 2. And this is 0 at minus I times 2. The 5 roots of the fifth degree polynomial. Here we have, find the roots of x squared minus ix equals 0. This one's easy. Common factor of x times x minus I. That equals 0 when either x is 0 or x minus I is 0. So the roots are 0 and 1. And then we're done. Okay, now